Okay, so can you see the lecture 11 clearly? Can you see the lecture 11 clearly?
Yes, doctor, we can see it.
Okay, thank you very much. Yeah. Okay, so lecture 11 will be a continuation from the lecture 10, which is on properties of Fourier transform. So we're going to continue now with the properties of duality, yeah, a duality. So what is meant by duality properties then? So let's have a look. Okay, if we have the xt signal in time domain here, so the Fourier transform will be the x omega, yeah, so the x capital omega, so that should be the Fourier transform for the xt. Okay, somehow there is a case whereby we cannot have the signals from the table, yeah, somehow we're going to have in time domain signal, time domain function, the terms of the signal is similar to these signals in frequency domain. So you can see that we are having the same pattern of signal. We have x capital also, but this return in time domain. Okay, you can see the difference now. Yeah, so the x omega and xt are the same terms of signals. The difference is only on the domain. Yeah, so we have omega and it's in time t. Okay, so interestingly, we can interrelate these relationship between this signal in time domain and frequency domain by using a duality properties. Okay, so based on this equation, if xt, which is having a similar terms with the x omega, but the difference is in domain, we can have a Fourier transform in which it will give us a 2 pi multiplied with x of negative omega, in which this x of negative omega, the terms of it will be same as the xt. Yeah, the term of x negative omega will be same as xt, but the difference will be on the domain. Okay, so you can see the relationship now. Yeah, so xt will give us x omega. So this xt, which is same as this term, yeah, will be having or will give us a 2 pi of small x negative omega, in which this x, small x or negative omega is actually same pattern. Yeah, the pattern is the same with the xt. Okay, so you can see the relationship now. Yeah, this is what we call as a duality, right? So to make it clearer for us, let's have a look at this example here. So we have a case whereby your yt is having these equations, which is a tau sin squared t tau over 2. And we are requested to find out what should be the Fourier transform for this yt. Okay, so from what we have learned so far, we can just refer to the table, yeah? So let's refer to the table whether we can find this kind of signal in time domain with a sin squared terms. Okay, so I'm now referring to the table. Okay, this is the table that we have. Okay, so there are two pages, that's what we have mentioned earlier, that give us the signals, yeah, the signals pair in terms of time domain and frequency domain. So referring to the left-hand side, this side, yeah, is there any signal with a sin squared terms in time domain? Okay, so far we don't have it, right? We have rectangular, we have a triangular, cos omega, sine, exponential, and end up with the exponential also. So we don't have any signals with a sin squared in a term in time domain. So how we can do this Fourier transformation? So we can then think of using a duality. So to use a duality, we have to refer to the right-hand side, which is its respective Fourier transformation for the left signals here. So is there any signals with the sin squared terms then? Okay, we don't have it so far. We have it here then, which is a transformation between a triangular in time domain and a sin squared in the frequency domain. So which means that a triangular function in time domain will give a sin squared function in the frequency domain. So we can use this pair to in a duality properties to find out what should be the solution for our previous example just now. So I'm going to use this pair of signals, yeah, between a triangular in time domain and a sin squared in frequency domain, yeah. Right. So let's have a look at the solution for this, for that example. Okay, this is the solution for that. Okay, so this is a duality properties that we have seen just now. Okay, so you can see the relationship here, yeah. So the xt is basically having a same term with the x omega. We just have a different in the domain, and as a result, the x negative omega and the xt will be the same, right? So in that case, this is from the table, yeah, from the table, which we state that, yeah, if we have a triangular t over tau, so I take this straight away from the table, yeah. So a triangular t over tau. So if we transform for it, will give us a tau sin squared omega tau divided by 2. So by applying duality, you can then write these terms in terms of time domain by simply change omega with t. So you're going to have this, right? So you're going to have a tau sin squared. So the omega is now changed to t. So t tau over 2. And then we can have its Fourier transform to be equals to, so see this one, we have 2 pi, right? So we have 2 pi here, and we straight away copy these terms here. We're going to have a triangular, so a triangular, and the t is now changed into negative omega. Yeah, so we have t over tau here, but for this particular case, it will be negative omega divided by tau, because we are referring to this, xt will be changed into x of negative omega. Yeah, so as such, this t will be changed into negative omega. Okay, so you understand that the duality properties clearly now, yeah, hopefully. Yeah, right. So we can see that if the signals is having this pattern, sin squared in time domain, so by using a duality properties, we are supposed to get this triangular function in frequency domain. All right, yeah. Okay, so let us go back to the question. What is the question just now? So simply, yeah, this question is simply give us like this: a tau sin squared theta over 2. You don't have a values, yeah. So straight away the answer will be this one. Huh? So basically, this example is to show you how to choose the appropriate signal to be used in a duality properties and how to apply a duality properties as a solution. Yeah. Okay. One more thing to be understood here is that basically the answer initially is negative omega over tau, right? But since we know that a triangular function is an even function, so it doesn't matter. We can still ignore the negative sign because the negative sign for the even function is meaningless. Yeah, so negative will be now equals to positive omega divided by tau. Okay, so the answer for these signals in time domain will be 2 pi a triangular omega divided by tau. Yeah, which is obtained by using a duality properties. Okay, all right. So let us proceed this example just to ensure that you really understand more, yeah, related to these duality properties. Let's have a look at this example number 2. Okay, this is the one. We are having a Fourier transform of a signal of xt given by this equation here. Yeah, initially it's xt. Yeah, xt. So it is now transformed into the Fourier transform. We give us x omega given as a 4 pi between these values. Yeah, omega less than 2 and omega bigger than negative 2. And it shall be 0 elsewhere. So based on this given question, number 1, you have to sketch the x omega. Yeah, sketch the x omega, and then you have to write the expression of x omega in rectangular function. Right, and number 2, you have to apply a duality properties of the transform and determine what should be the xt, or I can say what should be the time domain, yeah, the time domain of this x omega that you have produced in question number 1 here. Okay, hopefully you clear regarding the questions. Yeah, so you are given this x omega. Okay, with this value of 4 pi within this range of omega, first question, you have to sketch this x omega and then write it in terms of rectangular function. Number two, by having this omega in rectangular function, you need to find out what should be the xt or the time domain of this signal by using a duality properties. Okay, so hopefully you understand the question clearly. So let's have a look at the solution for this example now. Okay, this is the one. Okay, so number one, simply by having a 4 pi between given by omega less than 2 and omega bigger than -2, you are supposed to get the signals here, which is in rectangular pattern of signal 4 pi with the amplitude and range between -2 and +2. And from what we have learned previously in chapter 1, we can write that for this rectangular function, we're going to have the amplitude of 4 pi, yeah, and we are having a time scaling, yeah, in which you're going to have a 4 pi rectangular omega divided by 4. Okay, so that should be the mathematical representation of this x omega in terms of rectangular functions. Okay, so remember that that should be in frequency domain. Yeah, should be in frequency domain because you are given the x omega. Yeah, so that's why your answer shall be in omega terms. Yeah. Okay, so that is the answer for question number one. Straightforward, I believe. So number two, you have to find out what should be the xt. Okay, so for this particular case, again, we refer back to the table. So I'm now referring to the table. Is there any solution? I mean, is there any Fourier transform in the terms of rectangular? So let's have a look at page 2 and page 3. So from this list, we notice that there is no such signal in Fourier transform with rectangular terms, right? No such things, no such signals with rectangular terms. So we cannot use this table straight away, yeah, to find out the xt, yeah. But we can use a duality properties by simply referring to the left-hand side in which we have a rectangular as a time domain. Okay, so we can see that there's a rectangular function in time domain, and we can see that for this rectangular function, its Fourier transform is given to be in sync function. So by right, by using a duality properties, we can refer to the signals here. Rectangular in time domain will give a sync in frequency domain. So we're going to choose this pair of signals, yeah, as a solution for our problem. Okay, so let's have a solution for that. So now this is taken from the table, which if we have a rectangular t over tau signal in time domain, so its Fourier transform will give us this, which is a tau sync omega tau divided by 2. So we just take it straight away from the table. And now we can see that by using the duality properties, we can straight away copy these in time domain, but just change the omega with t. Okay, omega is now changed into t, and somehow the same things apply for the Fourier transform, in which we can simply copy these terms to the right hand side, yeah, in which a tau sync t tau over 2 will give us Fourier transform of 2 pi multiplied with a rectangular omega divided by tau. Yeah, so we just change t into omega and then multiply it with 2 pi. Okay, in this case, I simply ignore the negative sign because rectangular function is an even function, so negative sign can be ignored straight away. Yeah. Okay, so that should be the duality properties, in which if we compare these two terms here, because the question asks us to find out what should be the time domain function, yeah, the time domain function for this x omega, or in other words, what should be the inverse, yeah, what should be the inverse Fourier transform of the x omega. So that's what the question asks asked about. Yeah. So what should be the inverse Fourier transform for the x omega? So to find out the inverse Fourier transform for the x omega, we need to use a duality in this case. Okay, so what you have to do is to find out what should be the value of A and what should be the value of tau, such that once you obtain the A and tau value, we can substitute straight away into these terms in time domain and we can have the answer. Okay, so for that, we need to compare these terms 4 pi rectangular omega over 4 with the terms here, which is 2 pi A rectangular omega over tau. And once we compare it, we obtain that 2 pi A will give us 4, and this will give us A equals to 2, and tau value is equals to 4. So we're going to substitute these two parameters in these terms. So we're going to have the time domain signal of x omega, or the inverse Fourier transform for the x omega is 2 times 4, yeah, because A times tau is 2 times 4, sinc function of t 4 divided by 2. So that will give us 8 sinc of 2t. So that should be the inverse Fourier transform of the x omega. Okay, is that clear on the solution for this example? Any question on this question so far? No, yeah? Okay, if there's no question, I think we can proceed now with another properties, I believe. Okay, so the next properties to be covered is a differentiation, as stated in the slides here. So if we have xt function, which will give us x omega as its Fourier transform, we note that if the xt is said to be differentiated once, yeah? Okay, so we're going to have dxt over dt. So its Fourier transform will be simply a multiplication of the x omega here with a j omega. Okay, so that should be the case whereby we have a first order differentiation, yeah, of xt. So if we have a second, an n order differentiation, in this case is n order, so simply the Fourier transform will be j omega to the power of n multiplied with x omega. So in other words, we can say that if we have initially xt, which will give us the x omega, and xt is differentiated, yeah, so the answer for its Fourier transform will be simply x omega multiplied with the j omega to the power of n. So n is the order of differentiation. So if we have, for example, second order differentiation, this power of d squared xt over dt squared, so that will give us j omega to the power of 2 multiplied with x omega. Yeah? So that is the properties of differentiation. And the same things apply for the integration properties. If xt gives us x omega and xt is integrated, so this Fourier transform will be straight away x omega divided by j omega. So previously, if differentiation multiply with j omega, for differentiation it is x omega divided by the j omega. Yeah. Okay, so this is a properties of integration and also differentiation. So let's have a look at this example here, just to test our understanding on the properties of differentiation. Okay, so we are given this example, the ft signal, which is having this equation with respective time duration. We have positive 2t plus 4 between negative 2 and 0. And negative 2t plus 4 between 0 and 2. And elsewhere, the value of ft is 0. Yeah? Okay, so from the given ft here, we need to, number one, find the first and second derivative of the above function. Means that you need to find out what should be the first order and second order differentiation of the above functions. Yeah. Okay. Number two, once you have obtained this first order and second order differentiation, we need to find out what should be the Fourier transform of those first order and second order differentiation. Okay, so hopefully you understand the questions very well. We are given the FT. The first question is find first order differentiation and second order differentiation. The second question is to find the Fourier transform of the previous obtained first order and second order differentiation. Yeah. Okay, so let's have a look at the solution for this example. Okay, this is the case in which I have sketched this FT according to the given values. Yeah, so we have 2t plus 4 between -2 and 0. So this is the case, yeah, 2t plus 4 between -2 and 0. And then we have a -2t plus 4 between 0 and 2. So it's now sketched. Yeah, it's now sketched in this form to make it clearer for us. Okay, so from what we have learned before, we're going to have a first order differentiation for this ft. So when we differentiate a slope here, we're going to have a constant, yeah? A constant of 2. And then when we differentiate this slope, which is -2 value, we are going to have a constant of a -2. Okay, a constant of -2. All right. So this is the case, yeah? This is the case of your signals of ft. Right. So from that, we can say that the first order differentiation will give us this constant between -2 and 0. So that will give us a constant of 2. Yeah. And then from -0 to 2, we're going to have an amplitude of -2. Yeah. Amplitude of -2. Okay. And then if we base on this, sorry, I think I got a problem now. There's a monkey near to my house. Can we have a break for 5 minutes then? Sorry, yeah, there's a
Okay, doctor.
okay. Sorry for that, because I'm living in a kampong. I'm living in a kampong, so we have this kind of problem. Sorry for that. Yeah. Okay.
Yeah, don't worry, it happens.
Okay. Thank you. Okay, guys, sorry for that interruption from a group of monkeys. Terrible.
It's okay,
Ah,
doctor.
okay, very sorry about that. Yeah, sorry for this interruption. Okay, let us proceed again. Okay, so this is the case just now. This is a questions. I'm going to have a look at the solution for this. Let me see. Let me share you the slides. Okay, this is the one. Yeah. Okay. Can you see the slides clearly now?
Yes, doctor, we can see the
Okay,
slides.
good. Okay. This is the solutions, yeah? Okay. So for the second derivative, if we base on this diagram of the first order differentiation, when we differentiate this, I think I've taught you about this differentiation related to the step. Yeah, this is step function, basically a step function, which is a step from 0 to 2. So by right, we're going to have an impulse here at -2 and with the amplitude of 2, depending on the amplitude of the step signal. Okay, so we're going to have the first impulse at -2 with the amplitude of 2. And for the second case, when we differentiate this signal, we're going to have also a step from 2 to -2, yeah? 2 to -2, which is another case. So from 2 to -2, we are supposed to get an impulse, yeah? Because when we differentiate a step here, the impulse will be having a amplitude of -4, yeah, because the step is moving downward from 2 to -2, yeah. So the difference between these amplitudes is 4, so that's why we have the impulse due to this differentiation will give us -4, yeah. And then when we further proceed with this value at t equals to 2, when we differentiate it, yeah, we're going to have a step changes from -2 to 0. Yeah, -2 to 0. So when you differentiate this position, we are supposed to get an impulse of +2 amplitude. So the results of second order differentiation will give us these signals here. Yeah, so 3 impulses will produce as a result of this differentiation. Okay, so you got the point there. Yeah, so hopefully by this you have now understand the differentiation for the second order related to the signals here. Okay, so this is to answer the first question. So second question is to find out what should be the Fourier transform for these.
Doctor, uh,
Yes.
I still did not understand. Like, I understood the rule of differentiation and integration.
Yeah.
Either we multiply by j
Correct.
omega in
Mm-mm.
differentiation, but I don't understand it graphically, because we had a triangle.
Mm-mm.
I didn't understand. Like, should we multiply with the slope of the triangle? And what is the omega of the triangle?
Oh, okay. Okay. For this particular case, we are yet to arrive up to the Fourier transform. This is just in time domain. Yeah, time domain. If we go back to the question just now, it is to find out what is the first order differentiation and second order differentiation of the FT, in which the first order and second order differentiation must be in time domain. So what we did here is only in time domain. So we are yet to arrive up to the Fourier transform. So you get the point
So
there.
we differentiate the t
Yeah,
to t plus 4 in the respective of
time
t.
domain.
So
Yes,
we
correct.
got 2
Yeah,
and -2. So it's
correct.
normal differentiation.
Yes, that's
Okay,
differentiation in time domain.
sorry, so to ask too many questions, but uh, I, like we did just normal differentiation. We did not multiply with j omega, or is it something different?
J omega is a case whereby we're going to have that when we try to transform these signals in its Fourier transform terms. So basically that
Okay,
will answer your question after this, yeah? After this slide, I
uh,
think it will answer your question there, hopefully.
okay, thank you, doctor.
Okay, good. Okay, so this is the result in time domain, which is a results of differentiation, first order and second order. Okay, so the second part of the question, if we read the questions carefully, is the Fourier transform of this signal and this signal. Yeah, the Fourier transform of these signals, first order signal, and Fourier transform of second order differentiation signal here. So by right, you are going to get this expression for the DFT and the DT. Yeah, because we know that this DFT over the DT is a rectangular function. Okay, so by a knowledge of rectangular signal in terms of its scaling, in terms of its shifting, you are going to get the DFT. Supposedly, there should be two rectangular functions based on this diagram, yeah? So you're going to have, the first one is 2 rectangular t over 2 plus half. Okay, so the first term here is actually represented by this rectangular function. And then we have negative 2 rectangular t over 2 minus half, which is represented by this rectangular function. Okay, so now from this figure, we have write them in mathematical expression. Okay, so our task is actually find out what should be the Fourier transform of these signals here. Okay, so we're going to have for these questions, a rectangular t, okay, will be equals to sinc omega divided by 2. Okay, this is from the table that we have learned yesterday. You can refer to the table, yeah. Okay. We have to go back to this. Okay, A rectangular t over tau will give us A tau sinc omega tau divided by 2. So by substituting A and tau equals to 1, okay, we're going to have sinc omega divided by 2. That's why we have these equations here. Okay, so from what we have learned yesterday, we have to do a shifting first, and then followed by scaling. Yeah, followed by scaling. But for the amplitude scaling, you can do it anytime, yeah, because it won't give any effect, yeah. But in this particular case, I'm doing the shifting first. So rectangular t plus half will give us sinc omega divided by 2 exponential j omega divided by 2. Because when we have a shifting, it's simply multiplication with exponential terms. Okay, and then when we have a scaling now, which is rectangular t over 2 plus half, so that will give us these terms, 2 sinc omega exponential j omega. So if you cannot recall these Fourier transform results, you can refer back to our lecture 10 slides. Yeah? Okay, and then we have 2 rectangular t over 2 plus half. We're going to have 4 sinc omega e j omega. Okay, so and up, we're going to have also for a second terms here, 2 rectangular t over 2 minus half. So we're going to have 4 sinc omega exponential negative j omega. So this is the case, right? Okay, right. So basically from that, we're going to have 2 rectangular t over 2 plus half. So we're going to have 4 sinc omega exponential j omega minus sinc omega exponential negative j omega. So that should be the result of this differentiation for the first order. Okay, and for a second order, okay, for a second order, we're going to have this case, because we are referring to these signals here. Yeah, we're going to refer to these signals here. So from this, we're going to have that for d squared ft over dt squared, it is equals to 2 delta t plus 2, okay, which is the impulse at negative 2, with a negative 4 delta t and 2 delta t minus 2, which is the impulse at positive 2. So what we have to do is we have to find out the Fourier transform for these terms. So we're going to have 2 delta t plus 2 will give us 2 exponential j omega 2. Then 4 delta t will give us 4. This is based on the table, yeah, I'm referring to the table. So allow me to refer back to the table here. Okay, so delta t, if you base, I'm using this. So you have a delta t minus t naught, we're going to have a exponential negative j omega t naught. So if we have a delta t plus t naught, we are going to have a exponential positive j omega t naught. Yeah, so that's why we're going to have, for that term, it will be 2 exponential positive j omega with 2. 4 delta t will give us 4, and 2 delta t minus 2 will give us these terms. Yeah. So finally, for the second order differentiation, its Fourier transform is simply 2 exponential j to omega minus 4 plus 2 exponential j of negative 2 omega. Okay, so that should be the Fourier transform based on this method. So there should be another method, which is to use this signals transformation straight away, which is to be based on our properties just now. So I'm going to sketch the answer by using a Jamboard. Okay. Okay, then I'm going to share the Jamboard with you. Okay, so okay, you can see the Jamboard clearly, yeah? All right. So let us sketch the signals that we have in the questions just now. So we have this, right? We have this triangular function, which is 4. This is negative 2. And this is positive 2. So you can see my sketching here clearly?
Yes, we can see it, Doctor. We
Okay,
can see
good.
it.
Very good. Thank you very much. Okay, so let us write this in terms of a time domain. So basically, from what we have learned in chapter 1, that can be written as 4, okay, triangular function, okay, of t divided by 2. Am I right? Okay, so this is based on the time domain signals that we have that have been given the questions. Yeah. Okay, so in terms of a Fourier transform, so let me refer back to the table. So we're going to have then, if we have a okay, triangular t over tau. So the Fourier transform for this will give us, let me refer back to the table. Okay, it should be a tau sin squared, okay, sin squared omega tau divided by 2. Okay, so that should be the case. So when we have, this is from the table, yeah, so what I'm going to do now is I'm going to have the Fourier transform for these values, mean for this signal. So if we have then 4 triangular t divided by 2, so I'm going to have what then? So I can simply substitute the value of 4 and 2, which is a and tau respectively, into this equation. So I'm supposed to get 8. 4 times 2 is 8. Sin squared. Okay, so I'm going to substitute tau equals to 2. So end up going to have sin of omega. Okay, so you get the point there. So that should be the case when you have a 4 triangular t over 2. Its Fourier transform will be 8 sin squared omega. So let me see, yeah. So basically, if we have, I repeat the solution, I mean the answer for the previous slide. If we have 4 triangular t over 2, okay, so we are supposed to get the Fourier transform will be equals to 8 sin a squared of omega, yeah? Okay, that should be the case now. Okay, now we want to find out the differentiation, the Fourier transform for the first order differentiation for this signal, and Fourier transform for the second order differentiation for the signals. So we're going to get that if we differentiate the first terms here, I mean, if we differentiate the time domain signals, which is 4 triangular t over 2. Okay, this signals here when you differentiate it. Okay, so its Fourier transform, as what we have learned before, should be simply these terms that we have, these terms that we have here, yeah, multiply with j omega. So the answer will be j omega multiply with 8 sin squared omega. Okay, so you get a point there. And if we have a second order differentiation, let's say d squared dt squared, so of a 4 triangular t over 2. Okay, so the Fourier transform that we're going to get for these signals will be simply negative omega squared. Okay, why negative omega squared? Because when we j omega squared, when we have a square for j omega, we're going to have negative omega squared of multiply with 8 sin squared of omega. Okay, so that should be the solution based on this method. So if we compare the answer that we have previously, remember previously what we did is we obtained the signals. Yeah, we obtained the signals of a first order differentiation and second order differentiation. And then what we did is we produced the expression, and then only we find the Fourier transform for the signals, right? Okay, so this is second method in which we only need to know what should be a Fourier transform for the original signals, yeah, in which we get it as 8 sin squared of omega. And then to find the first order differentiation, to find the Fourier transform for the first order differentiation, simply we just multiply this Fourier transform with the j omega. And for the second order differentiation, simply we multiply the negative omega squared, which is j omega power of 2, with this at sin squared of omega. So the answer that you get basically will be the same. Yeah, the answer that you get for, let's say, this term, yeah, and also this term with respect to the, let me see, let me refer back to this slide. Okay, the answer that you get for this part, which is for the first order differentiation, and this part which is for the second order differentiation, the answer should be the same with what we have obtained before. Okay, is that clear on my explanation on these issues? So there are two methods now. The first one is by using this method, which is obtain the first order differentiation, then sketch the expression, yes, sketch this the results of differentiation, and then find the mathematical expression. Then only we obtain the Fourier transform, which is quite long, yeah. But the other method, which is easier, is based on what I've shown just now, in which you only need to find out what should be the Fourier transform for this original signal, and to find the first order differentiation, the Fourier transform of it, we will simply multiply the j omega with the Fourier transform, and then for second order differentiation, multiply j omega squared with the Fourier transform for these signals. Okay, which is easier then. So you have these options for differentiation. So is that clear on my explanation? Hopefully. Hopefully, yes, yeah? Okay, right. Now, let's have a look at the slides back. Okay. Okay, so then will be a convolution properties, which I believe, I think should be the last one. Yeah, that should be the last properties for today. Right, so for convolution, if we have these two signals here, where we have xt, which will give us x omega, and yt, which will give us y omega in terms of their Fourier transformation. So convolution between these two signals in time domain. So this is a symbol of convolution. I hope that you have read lecture 6. Yeah, you have tried to understand lecture 6, which is on convolution theory, right? So if these two signals are said to be convolved or having a convolution operation, xt convolved with the yt, so the Fourier transform for this convolution will be x omega multiplied with y omega. Yeah, so xt convolution is yt. In Fourier transform it will be a multiplication. I repeat again. Yeah, if two signals are having a convolution operation in time domain, so in Fourier transform or in frequency domain, it shall be simply a multiplication as shown here. Yeah. But if in time domain it is a multiplication, so in frequency domain it will be a convolution, yeah, between these two signals and need to be divided by 2 pi. Okay, so this is a convolution properties between two signals. Yeah, so hopefully you understand this clearly on convolution. Okay, so let's have a look at the solutions, these examples here. So we are having an LTI system used in valve control as shown below. The system is said to be injected with the input signal of xt, which is 5 over pi sinc of 5t, right? And it was noted that the feedback signal of h1 omega is 2 pi delta omega minus 100. Okay, so we are given this diagram. So the xt is the input. H1t is a feedback. Yeah, it's a feedback signal. And it was given here that h1 omega, which is a Fourier transform of h1t, is given by this expression. Okay, this is a Fourier transform for h1t. And then we have the output of yt. Okay, so the question is, you need to obtain the Fourier transform of the input signal. Okay, what should be the Fourier transform of the input signal? Number one. Number two, what should be the Fourier transform of the output signal of yt? Okay, basically, we are given the xt, so need to find out what should be the Fourier transform of it. We are given the h1 omega, and we need to find out what should be the output of, what should be the Fourier transform of this output yt. Okay, please note that based on the given diagram here, relationship between the input, the feedback, and the output is yt equals to xt multiply with h1t. Yeah, it's based on this multiplier or mixer yt. The output is xt multiply with the h1t. Yeah. Okay. So for that, let us see what should be the solution for this example. Okay, this is the one. Let's have a look. Okay. All right. So this is the case. Yeah. So I sketch the diagram for you. We are given this information. The xt as the input, and h1 omega is the Fourier transform of the h1t. Okay. So from the table, okay, let us have a look. We need to find out, yeah, the Fourier transform for this xt function, which is sinc 5t. So let us have a look at this table. Is there any such signal of sinc function in time domain? Okay, this is page 2. Page 2, yeah? So is there any sinc function in time domain based on this table? So there is no such sinc function in time domain, but we can notice a sinc function in frequency domain. It is for rectangular function. So now, to find out the Fourier transform for the sinc function in the question, we need to apply a duality properties. Because if you base on the question, your sinc function is in time domain. So as what we have seen just now, there is no such sinc function in time domain. The sinc function is only available in frequency domain. So we have to adopt a duality properties to find a Fourier transform of the xt. Yeah. Okay. So based on this, we are referring to the table which states that if we have a rectangular function, which is a rectangular t over tau, so its Fourier transform will be a tau sinc omega tau divided by 2. So now we can use a duality which states that if we copy these terms in time domain, we just change the omega to t now. We will have a tau sinc t tau over 2. So its Fourier transform will be A rectangular negative omega divided by tau. Yeah? So the t is now changed into negative omega, but since rectangular is an even function, we can ignore the negative sign. So that should be A rectangular omega divided by tau, and that will be multiplied with 2 pi. So this is based on duality properties. Yeah, so we just use it straight away. Okay, now in time domain, it is 5 over pi sin of 5t. So we need to find out what should be these terms. What should be the Fourier transform of a sin function. So for that, yeah, you are given the values. We have 5 over pi and 5 here. So we need to know what should be the value of a and tau such that we can substitute the a and tau in these terms. Okay, so for this, we note that when we compare the 5 over pi sin of 5t with the terms here, we're going to get a tau here shall be equals to 5 over pi. Okay, so we're going to have this. And further on, tau over 2 shall be equals to 5, yeah? Tau over 2 shall be equals to 5. So we compare it apple to apple, yeah? Tau over 2 shall be equals to 5. So end up, we're going to get that tau shall be equals to 10, and then the a constant of a, shall be equals to 1 over 2 pi. So once we have a and tau, we can substitute both of them into this equation. So supposedly, if we have 5 over pi sin of 5t, that will give us 2 pi multiply with 1 over 2 pi, which is the value of a, rectangular omega divided by 10, which is the value of tau. So end up the Fourier transform for 5 over pi sin of 5t is rectangular omega over 10. So this is based on a duality property. So that should be the answer, yeah? Rectangular omega divided by 10. Okay. So that should be the answer for first part. Second part is to find the Fourier transform for the yt. Okay, so you know that relationship between these three signals is yt multiply with is equals to yt is equals to xt multiply with h1t. Yeah. Okay, so we have this equation that relates these three signals yt equals to xt multiply with h1t. Okay, but you are given the h1t in terms of its Fourier transform. So what we can do now is that we can transform these signals, all of them, xt, yt, and h1t, into their respective Fourier transform. So we're going to get x omega, we're going to get h1 omega, and we're going to get y omega. But remember from convolution properties, yeah, when two signals are said to be multiplied in time domain, in frequency domain, it shall be a convolution. So that is why, if we base on this, in time domain, we're going to have yt equals to xt multiplied with h1t. So in frequency domain, when we transform them in frequency domain, so yt will become y omega, but this multiplication now will become a convolution. So that will give us 1 over 2 pi x omega convolve with h1 omega. Yeah. So this is to refer back to a convolution properties. You can refer to the slide, yeah, of convolution that I mentioned just now. Time domain, multiplication. Frequency domain is a convolution with additional division with 2 pi. Okay, so we know that the x omega from the previous part 1 is rectangular omega over 10. So we have this. And the h1 omega from the question give us 2 pi of delta omega minus 100. So basically, it is convolution between these two signals. So by now, I hope that you have understand what is meant by convolution. Yeah, convolution is a case whereby the signals will be shifted. Yeah, will be shifted accordingly. Yeah. So in this case, if we refer to these two signals, rectangular omega over 10, yeah. Okay, I allow me to use a Jamboard to explain this in the clear picture, yeah, in the clearer picture. Then, so allow me to use the Jamboard. Okay. Right, this is the one, yeah. So we have a signals of rectangular, okay, rectangular omega divided by 10. Okay, and then we have another one, if I'm mistaken, it is delta omega divided by 100. Yeah, basically this is signals which has been shifted by 100 units to the right. It is a convolution. Yeah, so it allow me to okay, this is convolution sign. Okay, let's have a look at the signals of this rectangular omega over 10. So from what we have learned previously in chapter 2 or chapter 1, sorry, rectangular omega over 10. So this is in omega domain. Yeah, so that should be basically a signals which is having an amplitude of 1, okay, and the duration of the frequencies will be from -5 to a +5, yeah, -5 to +5. Okay, so this is a rectangular omega over 10, and these signals shall be now convolved with this impulse function, which is located at 100. Okay, so that should be our impulse located at 100. Yeah, okay, that's the case. That should be the impulse located at 100. So it is actually a convolution between these two signals. So when we convolve these two signals, remember from what we have learned, from the lecture 6. Yeah, I give one example on lecture 6 on convolution. Okay, so you need to find out where is the position, the place where the two signals are said to be overlapped. Yeah, overlap with each other. So if we base on this, when we consider these signals located between -5 and +5, and these signals which are said to be located at 100, we can see that when we convolve these two signals, the results of convolution will be a signals which will be now shifted to 100. Yeah, which will be shifted to 100, in which the results for this convolution will be a rectangular function which will be now shifted to 100. Okay, that should be the case, in which the duration now will be from 95 to 105. So that should be your results of convolution between these signals, rectangular omega over 10, and these signals, which is the delta function omega minus 100. Yeah, so this convolution results will give us this. All right, so end up we can write the solution for this will be simply rectangular, okay, omega minus 100 divided by 10. Okay, so yeah, that's the solution for this example. Yeah, okay, so let's have a look at this answer straight away. Okay. Okay, so this is the case that I mentioned just now. You have 1 over 2 pi. Remember, here omega is 2 pi, delta omega, so it will cancel out. So end up, when we convolve these two signals, I mentioned in the Jamboard sketching just now, you're going to get these solutions. Yeah, rectangular omega minus 100 divided by 10. So simply, we just substitute omega with omega minus 100. Yeah, so that should be the answer for y omega. Okay, any question on this so far? Hopefully it's clear, yeah, on the convolution properties based on this example. Okay, let's have a look at more examples on convolution. Let me see, is there convolution examples after this or? Okay, so this is a mix properties of Fourier transform. So we are given this example here. By applying a properties of Fourier transform, determine the Fourier transform of the following signals. Number one is a GT of 3 rectangular 0.25t plus exponential negative 2 t modulus t. And then we have HT of sine 9 sin squared of 40. Okay, that should be the first question. Yeah, basically it's to find the Fourier transform. So you need to have a good understanding on to choose which signals, or you need to have a good understanding to apply which properties that you think suitable to be applied in solving this question. Yeah. Okay, I think let us proceed with this question number one first. Okay, to find the Fourier transform for GT and HT. Let's have a look at the solution. Okay. Okay, this is the case. Number one, your signals is a GT, 3 rectangular 0.25t plus exponential negative 2t. Okay, so simply we refer to the table, yeah? So we refer to the table. This is a straightforward question. So GT, when you do a Fourier transform, it gives us G omega. 3 rectangular t over 4, refer to the table, the signals, you're going to get 3 times 4 sin omega 4 divided by 2. And 3 exponential negative 2t will give us this, yeah? So this signals here, exponential negative 2t modulus, is basically referring to these signals, yeah? If we can refer, okay, it's basically referring to these signals here. A exponential negative A modulus t. So basically you have to choose suitable signals to be used, yeah, in the solutions. Yeah? So end up, we're going to have this answer for the G omega, a summation of these two Fourier transform, yeah? Okay, for this questions here, which is 9 sin of 4t, okay, for this you have to use a duality properties because you are given the function in time in t domain, in time domain is having a sin squared. So from what we can see on page 2 and page 3, there is no such time domain signal with a sin squared function, yeah? You can refer back to table page 2 and page 3. So there's no sin squared function in time domain. So basically you have to apply a duality properties to find the answer for that, in which you can use a pair of triangular signal with a sin squared signal. Okay, so this is from the table that will give us A triangular t over tau, will give us A tau sin squared omega tau divided by 2. Okay, so for this, you have to, we can copy this term in time domain. So that will give us A tau sin squared t tau over 2 in time domain. And in frequency domain, you are getting 2 pi A triangular omega over tau. Yeah. So again, although it's negative initially, but since triangular is an even function, we can just have a positive, yeah, positive omega divided by tau. Okay. So you have this pattern based on duality properties. So to find the answer, the Fourier transform for 9 sin squared of 40, simply you just substitute or you just compare the values to find A and tau. So the A and tau obtained can be substituted in these Fourier transform terms. So when you compare, you're going to get tau shall be equals to 8, yeah, because 4 is tau over 2, so tau equals to 8. And A shall be equals to 9 over 8. So once you have A and tau, you can then obtain that 9 sin squared of 40 basically will be 2 pi multiplied with 9 over 8. We base on this, and tau should be equals to 8. So end up, it should be 9 pi over 4 triangular omega divided by 8. So that should be the answer for this question. Yeah. Okay, straightforward now. I hope by now you have clearly understood the convolution, sorry, the duality properties clearly, yeah? Okay, so let's have a look at this solution. Sorry, there is no more examples related to the same slide just now. Okay, this is the one. You are given Fourier transform, sorry, you are given the xt in time domain of exponential negative modulus t, a cos of 10t. And this is the first one, you need to find the Fourier transform. The second question is to find the inverse Fourier transform. So you are given the y omega, you are given the frequency domain signal, you need to find out what should be the time domain signal, yeah? So that's the question it's all about. Okay, so let's have a look at the solution for this example. Okay, this is the one. Right, so we have a signals exponential negative t of cos of tan t. So notice that from what we have learned yesterday, when we have a multiplication with a cosine function, straight away we know that this must involve a modulation properties, yeah? Yeah, any signals which has the cosine terms, so it must involve a modulation property. So in mind, we know that to solve this question, we need to adopt a modulation properties. So by anyhow, we need to find out what should be a Fourier transform for exponential of negative t modulus. So by using a table, we can refer to the last signal, yeah, the last signals in the list. Exponential negative t modulus will give us 2 over 1 plus omega squared, yeah. So that will be based on the table. And then we know that this is for modulation properties yesterday. When we have xt cos omega naught t, and Fourier transform for this will give us half x omega minus omega naught plus x omega plus omega naught. Okay, in this case, our xt is exponential negative t, so that our x omega is this one, yeah? So by comparing these initial properties of modulation and this question, we can say that your omega naught will be equals to 10, and as such, the solution, the answer for transform for these signals in time domain will be 1 over 2. Okay, so x omega minus omega naught will be 2 over 1 plus omega minus 10. And for that, x omega plus omega naught will be 2 over 1 plus omega plus 10 squared. Okay, so that should be the solution, the Fourier transform for the signals exponential negative t cos of tan t, yeah? Okay, this is for the last one, the last question, which is y omega having 8 pi delta omega minus 5, 8 pi delta omega plus 5, need to find in its inverse, yeah, its inverse Fourier transform in time domain. So for this, again, it's straightforward. Yeah, we have to refer back to this table. Okay, so you can refer to the signals here. Yeah, so we can see that you have about the same relationship. Yeah, we have signals of 2 pi delta omega minus omega naught in the frequency domain. So its respective time domain shall be exponential terms, yeah? Exponential j omega naught t. So by comparing this value in time domain and frequency domain, straight away we can write that for 8 pi delta omega minus 5, its inverse Fourier transform will be 4 exponential j5t, and for 8 pi delta omega plus 5, its inverse Fourier transform will be 4 exponential negative j5t. So that should be the answer, yeah, the inverse Fourier transform for the y omega. Okay, straightforward, yeah, the question is straightforward, yeah. Okay, so let's have a look at another example before we end the class today, I believe. Okay, I'm not going to do this example, yeah. You can try to do this on your own, yeah, because this is to be based on convolution signals, convolution properties. Okay, just to remind you that if we face this kind of relationship, yeah, with this box here, we have the input, xt is the input, ht is the system equation, and yt is the output. So if we base on this relationship, we can see that the relationship between the input, ht and yt is a convolution, yeah? Yeah. So in which yt is equals to xt convolve with the ht. Okay, repeat that. If we face with this kind of system diagram, the relationship in time domain between the signals in this problem shall be output yt equals to xt, the input, convolve with the ht. Yeah, yt is xt convolve with the ht. So that should be a relationship between the input, the system equation, and the output yt. Okay, so please try to solve this on your own. If you face a problem with the solution, you can always PM me for a solution, yeah, or to confirm your answer later on. Okay, so let us proceed with the last example for today, which will end up our lectures on properties of Fourier transform. We are given the signals equation, a signals diagram. VIT is the input, HT is the system equation, and the output is V naught T. Okay, and given further that in frequency domain, if we transform for the V naught T is V naught omega, which is sinc of pi omega minus 4 pi, pi omega minus 4 pi. That should be the Fourier transform for the V naught T. Okay, further on, it is given that the VIT, the signals of VIT is basically a cosine function, it's a cosine function, but the VIT is limited between negative pi and positive pi. Okay, so this is a VIT, which is limited only between negative pi and pi. So it is a cosine function, cosine function, but a cosine function which is limited in time domain from negative pi to positive pi with the amplitude from 1 over pi negative to positive 1 over pi. Okay, so this is the question. So number 1, express the VIT given here mathematically in terms of rectangular function. Basically, if you base on this, it should be a multiplication between a cosine function and rectangular function. Okay. Number 2 is to determine the VI omega. Okay, so once you have the VIT, you must be able to find the VI omega. You need to find the Fourier transform of the VIT. And number 2, you need to obtain the V naught T. Okay, you are given the V naught omega, so you need to obtain the V naught T. So it means that you have to obtain the inverse Fourier transform for the V naught omega. Yeah. Okay, so let's have a look at the solutions. Hopefully you can recall the questions clearly. Okay, so the solution for this, right, so we are given this diagram just now. Okay, so this is your VIT given, and we know that this VIT in terms of its cosine function is equals to cos of 4t, and the amplitude is 1 over pi, so it should be 1 over pi cosine of 4t, because the amplitude is from negative 1 over pi to positive 1 over pi. Okay, and the frequencies or the period of these signals is pi over 2. So in such a way, we can write that in time domain, the signal is 1 over pi cos of 4t. But this is the case when the signal is having a duration from negative infinite to positive infinite. So we can adopt this equation. Yeah, but knowing that the VIT is limited only between negative pi and positive pi, so we have to multiply these signals of 1 over pi cos of 4t with this rectangular function between negative pi and positive pi, so that your cosine function here will be limited from negative pi to positive pi. So this rectangular function is having this equation supposedly, which is rectangular t over 2 pi. Yeah, hopefully you understand why we have this rectangular function with this scaling value 1 over 2 pi. Because why? Because your signals is said to be having a time value from negative pi to pi. That's why we have this scaling of 2 pi. Yeah? Okay, so for that, the VIT will be a multiplication between these two signals, which will give us 1 over pi cos of 4t multiplied with rectangular t over 2 pi. Okay, right. So the second question is to find the Fourier transform for the VIT. Okay, so for the VIT, since we have, this is the answer for VIT, and we have a cosine terms there. So by right, we must use a modulation properties to find the VI omega. Yeah. So what we have to do now is to find the Fourier transform for rectangular functions here. Okay, so for these rectangular functions of t over 2 pi, the Fourier transform will be 2 pi sinc of pi omega. So I hope by now you have understand how to obtain this Fourier transform. Yeah, if your time domain is rectangular function. Yeah, always refer back to the table. Okay, so knowing that you have the cos 40 terms here, as I mentioned just now, you have to adopt a modulation properties. So by then, you're going to get for cos 40 rectangular t over 2 pi, you are going to get 1 over 2, 2 pi sin pi omega minus 4, because initially we have these signals for rectangular t over 2 pi. So when rectangular t over 2 pi multiply with cosine of 40, you're going to get this. Okay, 2 pi sin pi omega minus 4 plus 2 pi sin pi omega plus 4, which is a result of modulation properties. Okay, and knowing that we have a 1 over pi terms over there, yeah, so end up finally, the results for this will be sin pi omega minus 4 plus sin pi omega plus 4. Okay, so that should be the results of your Fourier transformation. Okay, hopefully it's clear on the solutions here. And finally is to find the inverse Fourier transform for the V naught omega. Okay, so for this you have to, this is a solution in which you know that relationship in time domain and frequency domain. You have to refer to the table. I'm using a rectangular pair of signals. So in time domain is A rectangular T over tau. In frequency domain is A tau sin omega tau divided by 2. So seems to be similar here. Yeah, seems to be similar here. So by right, your V naught T shall be having a rectangular function. Yeah. So what you have to do is to compare the A and tau value, or to get the A and tau value. Yeah, so we can compare A tau with 1, tau over 2 with pi over there. Yeah, so when we compare, going to get tau over 2 shall be equals to pi, tau equals to 2 pi, and A tau shall be equals to 1, and as a result, A shall be equals to 1 over 2 pi. Yeah, since we have tau equals to 2 pi just now. Okay, so if we have a functions of 1 over 2 pi, yeah, I'm going to substitute pi and a into the equations above here. So 1 over 2 pi, rectangular t over 2 pi will give us sin pi omega, yeah, based on the given obtained a and tau, we're going to have this. But basically, if you refer to this, we have a shifting in frequencies, yeah. Your V naught omega basically is a shifting of frequencies. Although you have about the same pattern here, but additionally we have a frequency shifting of 4 pi. So as what we have learned yesterday, when we have a frequency shifting of 4 pi here, you have to adopt a frequency shifting properties in which based on this, if ft give us f omega, so if ft multiply with exponential j omega naught t, will transform be a frequency shifting of omega minus omega naught. Okay, this is from the properties of frequency shifting yesterday. So as such, we can say that we are going to get basically it should be 1 over 2 pi rectangular t over 2 pi multiply with exponential j of 40 here. So we're going to get sin of pi omega minus 4 pi. So the effect of multiplication with exponential j of 4 pi t to the above equation here will be on a frequency shifting of 4 pi. So that's why we have this as the answer. Yeah, means that this is the answer for a time domain of V naught omega, in which it should be 1 over 2 pi rectangular t over 2 pi exponential j of 4 pi t. Okay, so that should be a solution for the questions that we have here in this slide. Okay, right. Okay, so that's the end of lecture number 11. So we have done with lecture 11, or in other words, we have done with this